History remembers Frank Whittle as the father of the jet age. But while Whittle took the glory, a quiet genius named Hayne Constant was building the future. In 1936, the engineering world was divided. Whittle built centrifugal engines, rugged, simple, but wide and drag-heavy. Hayne Constant bet everything on the Axial Flow Compressor, a design that was thin, aerodynamic, and theoretically perfect. But there was a catch. Axial engines were unstable. To understand the magnitude of Constant's challenge, we must strip away the romance of flight and look at the thermodynamics. In the mid-1930s, Frank Whittle was championing the centrifugal compressor. It operates on brute force. It grabs air and flings it outwards against the casing to compress it. It is robust. It is tolerant of damage. But it has a fatal flaw. To get more power, you must make the engine wider. A wide engine creates drag. Drag kills speed. Hayne Constant saw this limit immediately. He argued that the future lay in axial flow. In an axial engine, the air does not change direction. It flows straight through, compressed by spinning blades, stage after stage. It allows for an engine that is aerodynamically perfect, thin, pencil-like, capable of piercing the air with minimal resistance. The theory was sound. The reality was catastrophic. The problem is aerodynamic instability. In an axial compressor, each blade acts as a miniature wing. It must bite into the air at a precise angle. If the airflow is disturbed, by a sudden throttle movement or a sharp turn, the blades stall. But unlike an aircraft wing stalling, which simply loses lift, a compressor stall reverses the airflow. The high-pressure air at the back of the engine violently escapes forward. They call it a surge. It is effectively an explosion inside the engine. Constant was not unearthed. He partnered with Metropolitan-Vickers to build the F.2 engine. It was a marvel of complexity compared to Whittle's simple device. It featured 9 stages of compression. It promised efficiency figures that Whittle could not touch. But the F.2 was temperamental. While Whittle's engines were powering the Gloster Meteor prototypes in 1941 and 1943, Constant's engines were destroying themselves on the test bed. Blades snapped, bearings failed. The surge seemed incurable. The pressure from the ministry was immense. The war was at its peak. Resources were scarce. Why waste money on the unreliable axial engine when Whittle's centrifugal engines were ready for production? Constant was fighting a war on 2 fronts, against the Germans and against the British bureaucracy that wanted to shut him down. He needed a breakthrough. He needed to prove the F.2 could fly. In late 1943, the F.2 was finally cleared for flight trials. It was mounted to a Gloster Meteor, serial DG204. Initial reports were promising. The pilots noted the lack of vibration. The fuel consumption was significantly lower than Whittle's engines. For a brief window, it appeared Constant had solved the puzzle. But the axial compressor is unforgiving. It waits for a mistake. January 1944. Squadron leader William Davey took DG-204 to altitude. He was testing the engine's limits. At high speed, the airflow into the intake became turbulent. The F.2 engines surged. The violence of the surge at that RPM was sufficient to shatter the compressor blading. The shrapnel tore us through the engine casing and severed the wing structure. The aircraft disintegrated. Squadron leader Davey was killed instantly. The tragedy confirmed the ministry's worst fears. The axial engine was deemed too dangerous for service. The contract was threatened. The F.2 program was effectively dead in the water. Frank Whittle had won. The centrifugal engine would power the Royal Air Force, but Hayne Constant refused to concede. He knew that the centrifugal engine was a technological dead end. He knew that if Britain abandoned axial flow, they would lose the future of aviation. He had to rebuild. He had to redesign the very concept of the compressor, and he had to do it while the industry turned its back on him. The F.2 was a failure, but from its wreckage, Constant was about to forge the Sapphire. The war ended with Frank Whittle as the undisputed victor of the jet race. His centrifugal engines were reliable, robust, and in mass production. They powered the Gloster Meteor. They powered the de Havilland Vampire. Hayne Constant's Axial project, by contrast, was in ruins. The F.2 catastrophe had stained the reputation of the axial compressor. The Ministry of Supply viewed it as a dangerous science experiment, not a weapon of war. But Constant remained dogmatic. He argued that the centrifugal engine was hitting a drag wall. To go faster, Whittle's engines had to get bigger. Constant's engines just had to get smarter. Metropolitan-Vickers, guided by Constant's research, went back to the drawing board. They couldn't change the laws of physics, but they could refine the aerodynamics. They produced the F.2/4, codenamed Beryl. The Beryl was a beast. It produced 4,000 pounds of thrust, nearly double the power of the early Whittle engines, while maintaining the same slim profile. It was the first proof that the fragile axial engine could actually produce raw power. The Beryl worked. It was powerful, but it was an orphan. The airframe it was designed for, the Flying Boat Fighter, was cancelled. Metropolitan-Vickers, a heavy engineering firm, decided to cut its losses. They were building power stations, not airplanes. They wanted out of the jet business. In 1947, they sold the entire division. This could have been the end. Instead, it was the turning point. The project was purchased by Armstrong Siddeley. Armstrong Siddeley took Constant's theories and Metrovic's hardware and poured resources into them that the previous team could only dream of. They took the Beryl design and supercharged it. They added more compressor stages. They improved the metallurgy. They created the Sapphire. The Sapphire was a revelation. When it ran on the test bench in 1948, it didn't just beat Whittle's engines, he humiliated them. It offered a thrust-to-weight ratio that the centrifugal engine physically could not match. The drag wall that Constant had predicted had finally arrived. As aircraft designers tried to break the sound barrier, they found that Whittle's fat engines were holding them back. They needed slim engines. They needed the Sapphire. The Sapphire became the heart of Britain's Cold War defence. It powered the Gloster Javelin, the heavy interceptor designed to shoot down Soviet bombers. It powered the Handley Page Victor, the strategic nuclear bomber. The United States, watching from across the Atlantic, realized they had fallen behind. They purchased the license immediately. In America, the Sapphire became the Wright J-65. It powered the A-4 Skyhawk and the F-84F Thunderstreak. Hayne Constant's dangerous experiment was now the engine of the free world. There was a fierce rivalry in the 1950s between the Armstrong Siddeley Sapphire and the Rolls-Royce Avon. Both were axial flow, both were brilliant. But the Avon eventually won the market war. Why? Was it simply better marketing, or did the Sapphire have a lingering technical flaw at high altitude? Let me know what you think. But the victory was bittersweet. By the 1950s, the entire industry had converted to axial flow. Rolls-Royce, who had initially backed Whittle's centrifugal design, quietly abandoned it and developed the Avon, an axial engine that looked suspiciously like the designs Constant had proposed a decade earlier. The industry had caught up to Hayne Constant. His radical idea was no longer radical, it was the standard. Constant was appointed director of the National Gas Turbine Establishment. He was no longer the rebel, he was the establishment. But the engineer in him wasn't finished. He had conquered the jet engine. Now he wanted to conquer the runway. He looked at the long concrete strips required for jet fighters and saw a weakness. If the Russians bombed the runways, the RAF would be grounded. He proposed a new, terrifyingly complex idea, the flying bedstead. vertical takeoff and landing. Once again, Constant was pushing for a technology that was decades ahead of its time. And once again, he would face skepticism, technical hurdles, and the immense danger of trying to make a jet engine lift its own weight dead vertical. The Sapphire had vindicated him, but his final project would push the limits of British engineering to the breaking point. By the mid-1950s, Hayne Constant had won the argument. The axial flow jet engine was the standard for the world. But Constant, now director of the National Gas Turbine Establishment, was not interested in victory laps. He was interested in the next impossible problem: runways. Constant saw the runway as a shackle. In a nuclear war, air bases would be the first targets. He believed the future of aviation was vertical takeoff and landing. The machine you are looking at is the Rolls-Royce Thrust Measuring Rig. It looks crude, but it is solving a problem of immense complexity. How do you balance 7,000 pounds of metal on top of an invisible column of gas? Constant and the engineers at the NGTE did not invent the Harrier Jump Jet directly. That glory belongs to the team at Bristol Siddeley. But they wrote the physics textbook that made it possible. They developed the bleed air stabilization systems. They proved that a jet engine could be throttled delicately enough to hover. While the Americans were experimenting with tail sitters, planes that landed vertically on their tails like rockets, the British approach, influenced by the axial flow efficiency Constant had championed, focused on vectored thrust. It was the ultimate vindication of the axial compressor. A centrifugal engine, with its wide girth and convoluted airflow, would have been a nightmare to package inside a VTOL fighter. The slim, straight-through design of the axial engine allowed the Pegasus engine to sit in the heart of the Harrier, breathing massive amounts of air to generate lift. Constant's fingerprints were all over the design, even if his name wasn't on the patent. So, we arrive at the central mystery. If Hayne Constant was right about the axial engine, and if his work underpinned the jet age and the vertical age, why is he not a household name? Why do we have statues of Sir Frank Whittle, but only technical papers for Hayne Constant? The answer lies in the brutal nature of industrial capitalism. Frank Whittle was the inventor. He had the patent. He fought the establishment. His story is a hero's journey, the little man against the system. Hayne Constant was the developer. He was the system. He worked for the government. He worked for heavy industry. History loves a spark. It rarely celebrates the slow, grinding process of turning a fire into a furnace. Whittle reads the match. Constantly built the fire. But if you want to see Hayne Constant's memorial, you don't need to visit a museum. You just need to look out the window at the airport. Look at the engine of a Boeing 787 or an Airbus A350. Strip away the high bypass fan and look at the core. What do you see? You see rows of compressor blades. You see air flowing in a straight line. You see the axial flow compressor. Every time you fly, every time you cross an ocean in hours instead of days, you are riding on the technology that Hayne Constant fought for. You are riding on the technology that killed William Davy in 1944, and the technology that was perfected in the cold testing sheds of Farnborough. Frank Whittle gave us the jet engine, but Hayne Constant gave us the world.